So we've already done the proof that an even number squared is always going to be even, and we showed that this was true. And then we asked ourselves, well, in this case, it's an even to the power of a specific even number, 2, right? Even to the power of 2. But then we asked ourselves, what if it's even to the power of any even number, not just a specific one like 2? And in this case, we found that this statement was actually false. It is not true that an even integer to the power of any even integer is going to be even, because when you take into account negative even numbers, any integer to the power of a negative integer is going to be giving you a fraction. And when you get a fraction, you can't have even or odd, because those have to be integers. Okay, well, if we know that it's possible to have an even number to the power of an even integer be even, but it's not possible for that to be true for all even numbers, specifically negative ones, well, maybe it's going to be true when an even number is to the power of a positive even number. So that's what we're going to look at today. We're going to ask ourselves, is this statement going to be true? First thing we should do with any problem, even though we've already seen 2 problems very similar to this, is still think of some examples, right, to verify that this is potentially true or not. So let's take our bottom even number to be 2, for example, and let's take it to the power of 2, 4, and 6, right? These are some simple powers and even integers we can choose. So let's see if the result is in fact even. Well, 2 to the power of 2 is going to be 4, 2 to the power of 4 is going to be 16, and 2 to the power of 6 is going to be 64. Okay, so I think this is true. Let's just verify this a little bit further by just changing the base number down here to the next even number. Maybe we can do 4, right? 4 squared, 4 to the power of 4. Let's not do 4 to the power of 6 because that's way too computationally intense. And this should be more than enough examples to think of in order to get a good idea of whether this is true or not. So 4 squared is going to be 16, and then 4 to the power of 4 is going to be 16 times 4, which is 64, and then 64 times 4, which is going to be 256, I think. If any of these are wrong, I'll correct them in post, but the idea is that these, in fact, do show us that potentially all even numbers to the power of a positive even number result in an even number. So we can now start, I think, writing our proof. Okay, so in order to start writing the proof, we need to figure out what it is we're actually proving, which we need a statement for. So what is our mathematical statement? Well, first we have to recognize this is for all even integers to the power of all positive even integers. So it's a for all proof. So for all a and b that are integers, and we're going to label this a and to the power of b. So we're going to say if a and b are even, then a to the power of b is even for, or we're going to say when b is greater than or equal to 2. Now, why did I add this last bit in? Because we haven't seen me add anything in at the end. Well, because we have to verify b is both even and positive, and the lowest possible even number is going to be, in fact, 2, right? So we have to make sure that we directly state in our statement that b does have a restriction on its lower boundary, that it cannot be less than 2. It has to be 2 or greater, and it must be even. Those are going to be the 2 conditions we have to ensure that our proof follows when we're writing it. Okay, so what is the actual proof going to look like? Okay, well, I'm thinking we can try proving this directly first, as you should with most proofs. I don't see a proof by contradiction making sense here, since we can clearly define even without needing to define like odd or anything else. Even the definition of even can exist independently. So let's try that. Let's try proving this directly. So how do we start? Well, it's a for all proof, so we always start with a let. So what do we let? We let some integers a and b exist where a and b are even. Then we should more explicitly define what it means for a and b to be even, or put them into some mathematical formula that we can actually use. So we can then say, so a is equal to 2m and b is equal to 2n. And because we've now introduced two more variables, we have to explicitly define those variables. So we have to define what we mean by m and n. So we have to say where, or let's say for some, since we've already said where, so for some mn that are going to be integers. Okay, fantastic. I think we've added enough substance now to start trying this and seeing if it leads to something looking even. So let's give that a try. So we can then say, then, comma, a to the power of b is going to equal to 2m to the power of 2n. And then what do we know about our power rules? Well, we can divide, well, this will be the same as writing 2m to the power of 2, all multiplied by to the power of, or sorry, all to the power of n. Why did I do it this way? You can absolutely switch the n and 2 around, but that's going to be a lot harder to compute. I think it's going to be easier to compute this and then look at this at the end, because we don't know what n is, right? We just know n is any integer. Actually, do we need to define? We do. We do have to say here, I just noticed, and n is greater than 0. Because in order for b to be even and for it to be positive, it has to be that this is true, so this makes it even, and n has to be greater than 0 in order for this to be positive, right? Okay, so we have to make sure we add that condition. Anyways, we can now write then, and then continue what I said down here. So what can we do here? We can definitely simplify this a little further. We can say that this is the same as saying 4m squared to the power of n. Okay. Next, let's, okay, I don't see a way to factor out a 2 and make that 2 to the power of some whole integer in a bracket, which is what we're going to be trying to do to show that it's equal to some even integer. I'm thinking we should maybe try and open the brackets up again, so we can say this is the same as saying 4 to the n multiplied by m to the 2n. Okay. Okay. Is there a way to factor out a 2 now? Trying to think. Well, with this, I'm curious, is this going to be the same as saying 2 times 2m squared to the n, right? That's what I'm wondering. And the reason I'm wondering if that's the same is because when we say 4m squared to the n, we're basically saying it's 4m squared times 4m squared dot 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 4m squared, and there's n of these, right? There's n of these 4m squares. So I'm thinking, well, you should be able to just factor a 2 out of all of these since they're all 4 times something. So you should be able to say this is the same as saying 2 times 2m squared times 2m squared times 2m squared dot 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 2m squared. And there's going to be n of these 2m squares. That's what I'm thinking. So let's maybe give that a shot. So what we're going to say is this is going to be the same. Oh, let's use the original color we're using for our proof here. This is going to be the same as saying maybe 2 times 2m squared to the n. So I think if it's true that I can do this, so we don't really need to add this step, but if it's true that I can do this, then we can just argue that this here is an integer and 2 times any integer is even. So that's all I really have left to do to show that this is even. However, I know that this is definitely equal to this on the left-hand side, 4 to the power of n times m to the power of 2n. I know this is definitely true, and I think I can say this. So let's try and just verify that these are in fact equal to each other. So what can we do? We can definitely open the brackets up here. So this is going to be 2 times 2 to the n times m to the 2n, okay? And we're gonna have still a 4 to the n times m to the 2n on the left-hand side. Okay, are these equal? I think so, maybe. Well, let's plug some n in, right? Maybe that'll help us. So let's try n is equal to 1. So then we're going to get 4 to the 1 times m2 to the, or m to the power of 2 times 1, which is just going to be equal to 4m squared. Okay, and then on the right-hand side, or let me write that down below, 4m squared, is that going to equal to this? We're going to have 2 times, or let me write that above, 2 times 2 to the 1 times m to the 2n, which is in fact going to be equal to 2 times 2, which is 4, times m to the power of 2 times 1, which is m squared. Okay, so for n equals 1, this is true. Is this going to be equal to n equals 2, I'm thinking? This isn't really a proof. This isn't a very good way of verifying it, but I'm struggling with figuring out how to show these are equal without using set theory. So let's try n equals 2. n equals 2. This would be 4 to the 2 times m to the 2 times 2. And is that going to equal to 2 times 2 to the 2 times m to the 2 times 2? So what are we going to get? We're going to get 16 m to the 4. And over here we're going to get, oh yeah, okay, these aren't equal. We're going to get 2 to the power of 2 is 4, times 2 is 8, multiplied by m to the 4. Okay, we can divide both sides by m to the 4. And then we're going to get 16 is equal to 8. And we know this is not true, which means that this relationship cannot hold for all n greater than 0. Oh, I should have tried 0 as well. Maybe that would have been easier. No, 0 would have just made everything 1. Or 0 actually would have worked here, because 0 would have made all of this 1 equals 2, I think. Well, the point is we found a reason for this not to be true, so this can't be true. And there's no way of, so we know this right-hand side statement isn't true, but we know the left-hand side is true because of power rules. Okay. So is there a way to factor a 2 out of here, I'm wondering? We've already seen I can't just say this is the same as 2 times 2 to the n. Okay. I don't think we can prove this directly, because I don't think it's possible to factor a 2 out of this. And the one method I tried showed that it's not the same as this for all n greater than 0. Okay. I'm thinking a direct proof won't work, so the next proof I'm going to try, because a proof by contradiction doesn't make sense here, we're going to try a proof by induction, because one of our variables is restricted under an inequality, like b has to be greater than or equal to 2. So this is a sign that maybe an induction proof might work. So let's give that a shot. So for the induction proof, I'm going to keep our let statement, because this statement is something you're going to have to make regardless of what kind of proof you're going to do. So we're going to say let a and b be integers, where a and b are even. So we've supposed our p. I am going to also define what we mean by, I'm going to define what we mean by a maybe, because I can see how we're going to be using the definition of a in the base case and the induction step more than once. So we can say, so a is equal to 2m for some integer m. Okay. First thing in our induction step is we're going to do the base case. The base case is going to be when b is equal to 2. So b is equal to 2. So we say let b equal to 2. Then we can say a to the power of b is equal to a to the power of 2, And then we can plug our definition in for 2 is going to be 2m to the 2, which is going to equal to 4m squared, which is going to equal to 2 times 2m squared. Fantastic. We got 2 times 2m squared. All that's left is to see that this is simply going to be an integer, because an integer to the power of 2 is still an integer, times 2 is still going to be an integer. So we can just explicitly state where 2m squared is an integer, so a to the power of b is even when b is equal to 2. Fantastic. So the base case is true. That's good. Now we're going to do our induction step, which is going to be the following. Induction step. Now in our induction step, we're going to create a new variable. We're going to say let k be an integer such that k is going to be greater than or equal to 2. So k is kind of like our b here. And a to the power of k, so k is an integer, k is greater than 2. A to the power of k is even, so a to the power of k is going to equal to 2q for some q that's going to be an integer. Okay, we've basically just said, let's suppose that k is an integer, k is greater than or equal to 2, and a to the power of k is even, and which means you can write it as 2 times an integer. Great. Maybe I should write suppose k is an integer instead of let, but should be the same logically. Now, what do we want to show in our induction step? Well, this is our induction hypothesis here. I'm just going to call it IH. What we want to show is, that a to the power of k plus 2 is even. We want to show that if you can find an a to the power of k that's even, the next even k is also going to be even. Which also reminds me, I've made a tiny mistake here. We're going to want to say that k is even, such that k is greater than 2. Yeah, okay, let me quickly rewrite that. We've better now defined our k. It's an integer, it's even, it has to be greater than or equal to 2. A to the power of k is even, so a to the power of k can be written as 2 times an integer. Great. Now I just want to rewrite that. We want to show that a to the power of k plus 2 is even. Why am I doing plus 2? This is why I thought of making sure to say that k is even. Because we're looking at powers of even, we're looking at a sequence of even positive integers. Well, what does that look like? We're looking at the following sequence, right? We're looking at 2, 4, 6, 8, 10, so on and so forth, right? And what do you notice? Well, what we're saying here is if you find a k, we're going to suppose a to the power of k, and let's say k is 4, is going to be even, right? So this is going to be our k. Well, what we're basically wanting to show is the next even integer over, which is simply going to be 4 plus 2, right? That's how you get the next even integer. This is also logically going to be even as well. That's basically the argument that we're going to be using here. That's why I'm saying plus 2. In fact, I think I'm going to quickly prove this as well for the reader. They might not be convinced that the next even integer is going to be the previous even integer plus 2. So let's quickly show this. We're going to write because an even, or let's say because any even integer plus 2 is still even. So we're going to do a proof within a proof briefly here. We're going to say, let's quickly prove this statement over here. Any even integer plus 2 is still even. That's the proof we're going to be writing here. I was going to say maybe we want to say because every consecutive even integer is plus 2 of the previous even integer, but that might have been an even more complicated statement to try and prove, I'm thinking, so I'm just going to prove this. This should be sufficient enough. So I'm going to say suppose any integer x, so suppose x is an integer such that x is even, so x is equal to 2y for some y that's going to be an integer. Okay, fantastic. Then we're going to say x plus 2 is going to equal to 2y plus 2, which is going to equal to 2 times y plus 1, right? We can just factor a 2 out. And now we have to acknowledge that y is an integer, plus 1 is still going to be an integer. So we say where y plus 1 is an integer. And then we can just conclude that since x plus 2 is equal to 2 times y plus 1, then x plus 2 is even. Okay, fantastic. So now we've proven what I've underlined here in blue. I'm just going to actually make this a nicer blue line quickly. Okay, that's the nicest blue line I'm going to be able to write. If this bothers you, that sucks. Okay, now we can actually get to our induction proof. We want to show that a to the power of k plus 2 is even. So where do we start? We can say, therefore, a to the power of k plus 2 is going to equal, now remember your power rules. This is going to be the same as saying a to the power of k times a to the power of 2. Now, the reason I consciously went from here to here instead of saying this is equal to 2m to the power of k plus 2, why did I not do this down here? Well, because when you're doing your induction step, you want to get what you supposed in your induction hypothesis. You want to get a to the k. So then you can plug in a to the k. And why do we want to do that? Because we have no idea what k is here, right? Like, I have no idea what this is. I don't know what that means. I could, of course, then just go back and say this is equal to a to the k, but why do that extra step? That's not very efficient. So let's just keep a, because what do we want to see? We want to get a to the k is equal to 2 times some integer. So we probably want to keep a to the k. So what can we do here? Because I didn't plug in our a yet, I can immediately say, well, notice a to the k is just equal to 2q. So we can write that down, multiplied by a squared. And hey, now we no longer have a power we don't know, right? We didn't know what k was, and we were able to get rid of it by replacing it with our induction hypothesis. What we do know is what a to the power of 2 is, right? When we plug a in. So let's quickly do that. Let's say this is equal to 2q times 2m to the power of 2. And we can easily compute this. This is simply just going to be the same as 2, my marker, there we go, 2q times 4m squared. And we already have 2, and we probably can just say this part here, excluding the 2, is going to be an integer, right? We can say that an integer squared is an integer, then that multiplied by 4 is still an integer, and then that multiplied by another integer is still going to be an integer. So we can say where q times 4m squared is going to be an integer. So a to the power of k plus 2 is even. Awesome. We have now shown that the very base case, that this statement is true, that an even to the power of a positive even is going to be even. We then supposed, okay, well, if there definitely exists one, for example, the base case, we're going to suppose that for any single even power, positive even power, it's going to be true. Will it be positive for the next even power? And if we can prove that it'll be positive for the next even power, it'll be positive. This rule for the next positive will be true until infinity, right? It'll be true until from 2, 4, 6, ... all the way until infinity for our even integers. So we can now conclude that because the base case shows the statement is true and the induction step shows that the consecutive even power is going to be true, then the statement must overall be true for all A and B. So we can then say, let's just erase the A here. In conclusion, since the base case and induction step each show the statement to be true for a even positive power, and then all of the consecutive, oh, my spelling is getting a lot worse. I think that's how you spell that. So we're going to say because it shows that it's true for an even positive power, and then all of the consecutive even positive powers, the statement is true. Of course, if you want to be explicit, you can just into here type in what your original statement was that you were trying to prove. But fantastic. We have now proven that any even integer to the power of any positive even integer is always going to be even.